So today I'm going to talk about the work that I have been doing since last three years, and this work I did when I was postdoc in Hall-Vinen-Bekarevich-Khalatnikov group in Brazilian Institute of Science, and so we published two papers in this work, one in Physical Review B, and another one recently we published Journal of Low Temperature Physics. Some part of the work Itamar gave here only as a part of Chandrasekhar lecture. But little bit I'll discuss that part, and then we made some extension of that work. So I'll discuss those things in a more elaborate manner. So this is the plan of my talk today. I'll basically motivate you with some recent experiments in this superfluid turbulence, which have brought some sort of revolution in this field after many years. And this experiment was done by a very familiar face from here, and Professor K.R. Srinivasan group in University of Maryland. And motivated by those experiments, now that has motivated a lot of numerical the people to basically come up with the explanation of those things. And basically the model, the sort of model what we are using in this field, there are many models, but we will be using mainly the two-fluid model. I'll discuss the details of all these things as I go along. And another problem with this system is that dynamical equations are not well defined. Although it looks like that two-fluid model will be able to capture the dynamics, but I'll convince you that there are some subtleties with the system which makes some sort of closure problem. And another problem comes here that how to characterize the turbulence behavior, because the turbulence behavior is not the same as the classical one, because here I'll show you that vortices are quantized and turbulence basically appears due to that. So how to characterize those turbulence behavior, and for that we need to basically know about how dense the quantized vortices are in the system, and those are dynamical in nature. So those things are needed for the clear explanation of this problem. And long back in 1950s, Joy Winan, he's an experimentalist who is also pioneer of this field, who proposed this dynamical behavior of how the quantized vortices will evolve with time. And recently, using the numerical simulation, we have basically modified that scaling. So I'll propose some work related to that. Then another subtleties right now in the numerical simulation is that we are not considering the full problem. We consider one component that is the normal component in the system that is frozen in the system, and in presence of that we see the evolution of quantized vortices. Right now we have also performed a simulation using the coupled dynamics, and so I'll discuss some of the interesting results that we have got recently. So to motivate you that already you might be knowing all these things, but just to give you the quick introduction, that the superfluid helium is not a new field of research. It started in the beginning of the 20th century when Cameron Ons from the same place from where Richard discovered were able to liquefy the helium at very low temperature. And then Kapitsa and Allen and Meissner, they were both working in the separate places, and were able to prove that superfluidity in helium below a certain temperature, that is 2.1 Kelvin. So this is the phase diagram of superfluid helium. So above this temperature, it just acts like a classical fluid. So we can understand everything using the Navier-Stokes equation and whatever information we can get about that. But as it crosses this line, which is near about 2.1 Kelvin, then it enters into the another phase where it is a mixture of two components of the fluid. One is the normal component, which have the usual viscosity and usual behavior. Another one is the superfluid component, which have little bit different behavior. Different behavior in the sense that the circulation of the superfluid component is quantized. And it can take some integer number value of this particular number, that is the diffusivity. And moreover, it is found that this quantization number is also fixed, that is n equal to 1. So what we see that vorticity magnitude corresponding to the superfluid component is always fixed. Interestingly, what is being observed that the ratio between the superfluid component density and the normal fluid component density that increases as one decrease the temperature. So at finite temperature, always we expect in this region that both the component will be present. But at 0 temperature, we'll have presence of only superfluid component. So the realization of this two fluid component, I mentioned to you that has been basically verified very recently in the experiment by K.R. Srinivasan, Daniel Lathrop, and group members. And in that, basically, they started with the two fluid. They started with the mixture of hydrogen and helium. As they cool down the mixture below lambda Tyson temperature, the helium goes to the superfluid phase and it remains in the liquid state, but hydrogen gets solidified and it acts like a tracer particle. So the hydrogen particle gets trapped on the quantized vortices, and they are able to clearly visualize this vortex and the vortex reconnections. You might have seen the movie several times, so I'm not going details of the experiment. Then we performed the simulation in order to understand this thing, and the turbulence in superfluid was long proposed by Richard Feynman, that turbulence is coming due to the quantized vortices and there might be reconnection between the vortices. And the first time the experiment was performed by Hall and Winen in long back 1956, and they basically confirmed this thing in the laboratory experiment. And so just to make the distinction between the kind of turbulence we get in normal superfluid and normal fluid, generally in the normal fluid, that the energy cascade happens by the eddies, and nonlinear interaction basically helps to cascade the energy from one scale to another scale. And there is a small scale, Kolmogorov scale, where the energy gets dissipated. In superfluid, we know that there is no viscosity for a superfluid component, so there is no dissipation source, molecular diffusion source. But what happens that the vortices gets there is a reconnection between the vortices, and that leads to basically some sort of instability on the vortices, and eventually that frequency corresponding to that keeps on increasing and it emits the phonon waves, and that leads to the dissipation. It is again an area of research. It is not quite confirmed thing. It is one of the model. So what I will be talking about, the main motivation of our experiment, the study comes from this particular experiment that is called the counterflow turbulence. So in that case, what happens that superfluid below lambda Tyson temperature, it is heated from one side and keep cooled at the other side using the helium bath. So what happens that superfluid doesn't have any entropy because it is generally in the ground state particles. So it doesn't respond to heat, but the normal component will start flowing in the direction of the applied temperature gradient. So it will just like a pressure difference. So in that direction, it will start flowing. To conserve the mass, the superfluid component will start moving in the opposite direction. So now there is a relative counter velocity between these two components that basically leads to this turbulence behavior, So as one keep on increasing this temperature gradient, they find that the turbulence basically fluctuation, it keeps on increasing. So we will be basically discussing this problem through our numerical simulation. Interestingly, as I mentioned to you that there are two components in the fluid, but those are immiscible components. You cannot separate these two components. So what is being observed that at very low heat flux or the temperature gradient, the normal component remains laminar, but superfluid component goes to the turbulent state. And at this point, we can see some discontinuous jump. So here what happens that both normal component as well as superfluid component go to the turbulent state. So this is quite different from what we experience in the classical fluid, because here on this one will have to understand the internal dynamics between the quantum fluid and the classical fluid in order to explain this one, and also the parameters which one will basically construct same like Reynolds number is not quite well defined here. So generally we use several models in this field in order to characterize the system. One is the Gross-Pitaevskii model, but again this model is used only at t equal to 0 when we have presence of only superfluid component. Right now, no theory has been developed in order to explain, take into account of the normal components. So here, the superfluid state is explained by a wave function, macroscopic wave function, and the probability amplitude will be given by the square of this particular wave function. And one can basically get this Euler kind of equation where one extra term will be present that is called the quantum stress, and that is solely coming due to the quantum nature of the fluid. But this model is not quite applicable at finite temperature, so this we are not using. I'll be mainly discussing about the model that is to the vortex filament model. As I showed that the vorticity magnitude of superfluid is fixed, so it has just like a structure of the Biot-Savart. So velocity is just like a magnetic field, and vorticity just like a current density. So if you know the current density or the vorticity, we can compute that what will be the corresponding the velocity. Then what happens that here we assume that vortex has this filament kind of a structure. It didn't have any core radius, and the one orientation of the vortices are made with several discrete points. And when two anti-parallel vortices come closer to each other, and if the distance between these two vortices are of the order of the separation between the points, then there is a reconnections. It means that they will exchange the segment with each other, and that will lead to the change in the topology of vortices. And so this is the reconnection through which the topology changes and eventually turbulence appears in the system. So here mainly we'll be interested to deal with the dynamics in presence of the normal components. So right now what we'll do that we'll keep the normal component quite frozen with time. So we have considered here that normal component is like it has a parabolic profile, mean profile is parabolic in nature, and in presence of that we want to study the dynamics of the superfluid the component. So in presence of the normal component, there will be two forces acting on the quantized vortices. One will be the drag friction force, which will be proportional to the relative velocity between the normal and superfluid component. And there are some temperature dependent coefficient parameters and diffusivity. And the another force will be the Magnus force. And since we are considering the quantized vortices as filament kind of a structure, so it will not have any inertia. So these two forces will be 0, and then we get this dynamical equation corresponding to quantized vortices in presence of the Gaussian normal component. So what are the length scale present in the system? And one length scale is it coming from the diffusivity, that is the quantized circulation of the individual vortices. Another length scale that appears in the system is the inter-vortex separation, because as we see in the right figure, that this is in the turbulent state, so the vortices are quite well tangled, so that inter-vortex separation basically becomes smaller and smaller, so that basically we can characterize that we are getting turbulent superfluid behavior. And another length scale is the length scale of the box. So there are 3 length scales present in the system. And that makes life a little bit complicated in the sense that how to characterize the turbulent behavior, which length scale we should use in order to quantify how much turbulent fluctuation we have in the system. So generally, it is being quantized by looking the total length of the vortices present in the system. So total, that is basically characterized by the vortex line density and the density. This is the total vortex length per unit volume of the box. So to describe this system, long back Landau and Sijap proposed this two-fluid model, but that two-fluid model was proposed in order to describe the superfluidity in helium, not the turbulence. And later on, Hall-Vinen-Bekarevich-Khalatnikov basically added this mutual friction term in this two-fluid model. And this mutual friction term is basically depend upon the relative velocity between normal and superfluid component, and the quantized vortex and the magnitude, and this mutual friction parameter that depends upon temperature. And from experiment, we have the idea about these parameters. And if you do a little bit calculation, what we find that it is proportional to this the vortex length density that I introduced in the last slide, and the relative velocity. So what we see here, that we have the superfluid velocity equation that is governed by this Euler kind of equation. This extra term basically takes care of the exchange of momentum between superfluid component and the normal component. Another factor is coming this vortex line density. So that can also evolve with time. And generally we see in our simulation that really changes with time. So I'll basically show you one movie, one of the animation related to that. So here what we see that we start with this the vortices, which is quite sparse, quite regular vortices. With time it come closer, there is a reconnection process, and after some time it becomes quite tangled with each other, and in that time also it evolves. So we need to take into account of the time evolution equation for this vortex line density in order to close that equation. So that was the main concern, and that was main motivation for us also to find out the dynamical equation. So long back, so in order to proceed that one, Winen basically asked very simple question that what we see here, that there is a vortex reconnection, then it breaks, and sometimes the length of the vortices will increase, sometimes it will decrease. So there are some production process associated with the vortex line density, and there is a decay process associated with that. So he argued basically that what will be this production rate and what will be this decay rate, simply on the basis of the dimension analysis that we always do in the turbulence. So we can see that diffusivity has the dimension of meter per second, And this vortex line density, which is the total length of the vortices per unit volume, has the meter per meter square dimension. So on that basis, he constructed these two quantity. But as we always encounter this problem that we don't know the nature of this non-dimensional function. And because it may have the dependence upon some non-dimensional parameter that we don't know. And that we'll have to get either from some experiment or some numerical simulation. So on the basis of numerical observation, he proposed that it will go like x to the power half, where x is this vortex length density, and then production rate will have this power law 3/2. But he could not rule out this behavior also. So both were possible, and it was quite debatable for a long time that which one to basically consider in order to understand the dynamics of the vortex and this. But that was proposed for the homogeneous and isotropic turbulence, and as we always see, that the problem comes when we start dealing with this inhomogeneous flow. So we have performed the simulation in case of the wall-bonded channel flow, and in that case, we considered this parabolic Filament-Poisson profile for normal component. And this was kept constant with time. And in presence of that, we see the evolution of quantized vortex. So using that thing, what we find that in presence of the wall, that equation gets modified. And we have some flux also comes in the picture because we have two walls along the vertical direction. So there is flux associated with that. And due to that, this production and decay term gets modified, and we get the different scaling for the production and decay term. And apart from that, in Wien equation, this part was absent. And we were able to get this flux through our numerical simulation. So first, what we did, I'll not go into detail, but we did some analytical things considering the fact that it is made with the discrete points. There is some arc length associated with that. And there is a curvature, and this is the tangent line. So curvature changes whenever there are reconnection process take place. So on that basis, basically we come up with this, what will be the form of this flux term, production term, and decay term in terms of the microscopic quantities. It means that what will be these terms in terms of this curvature or this arc length and the tangent at that point. And then basically we perform the simulation. In that basically we solve this equation corresponding to vortex quantized vortices in terms of this parabolic profile of the normal component using Runge-Kutta fourth order method. And we consider this the rectangular channel in which it is bonded in this vertical direction of the flow, and we consider the various flow values, 1 centimeter, 1.2, 1.5, that is being, this is a realistic parameter as being taken in the experiment also. And for various temperature, we perform our simulation for 1 Kelvin, 1.6, 1.9, and there is no proper vortex reconnection in vortex filament method model. So here we reconnect the vortices by hand. So suppose these 2 points will come closer to the intervortex distance, then we basically change, we use some technique and change this segment. And we are using right now dynamical criteria for reconnections. So this is the steady state profile of our vortex tangle, and using that we have computed the vortex line density profile, how it looks in the channel. So clearly what we see that the most of the vortices are basically accumulated near the wall in the wall bonded flow, but as we see the relative velocity between the normal and superfluid component, that is minimum near the wall. So that is quite interesting, where we have the minimum relative velocity, there we get the more accumulation of the vortices. And using that basically we compute different terms that I described to you. So here P1 and P2 correspond to the Wien form, and P3 is coming from our analytical result, and numerically then we computed, and we find that our numerical simulation is very much consistent with the form that we have predicted for the production of the vortex line density. And same is true for the decay of the vortex length also. Obviously, decay will be maximum where we'll have the maximum vortex line density. So this is consistent. And interestingly, then we get that since most of the vortices are accumulated near the wall, so we always get the flux in that direction. So positive flux in the positive side of the wall and negative flux in the negative side of the wall. That will lead to that accumulation. So this part was missing in the literature, and we were able to basically modify that relation. But as I told you that there was limitation in our model, we considered that normal component was not evolving with time. It was frozen with time. So then, as I mentioned to you that there are two states of turbulence. One is T1, another one is T2. In T1 state, normal component remains laminar, but superfluid component goes to turbulent behavior. So it is okay to take normal component as a laminar profile. So what we did, what we did in this case that we removed the nonlinear part from the equation. We consider the 1D normal component flow, and in that case we have taken this mutual friction term. That will basically make sure that there are some exchange of momentum between superfluid component and the normal component. So what we do that we evolve the system, first evolve this system of superfluid, then we take the time average, and then we compute this mutual friction term using this relation that we put in this equation, and then we evolve this normal component. Because these are scale separated phenomena, because this phenomena is much quicker compared to this one. So we consider in this way, and then we basically see that what happens to that normal component profile, how it affects to the normal component profile. First thing what we realize here, as we can see from here, that this Vn0 correspond to that when we don't have any coupling between normal component, it means that back coupling. It means that superfluid component doesn't affect to the normal component. This is the parabolic profile, and this is the profile that we get when we have the coupling. For the same temperature, but we are forcing here right now in order to get that same mean value. So what we get here that mutual friction this relative velocity doesn't change much. Same thing we get with the vortex line density. So whatever behavior what we got when we consider that normal component was frozen, that is correct. There is no problem with those dynamical equation. But as we look at the normal component profile, because when we consider that it was frozen with time, then there was no change in the shape. So it remained parabolic throughout all the time. But here, interestingly, what we find that as we keep on increasing the pressure difference, that is equivalent of increasing the temperature gradient in the direction, then it flattens in the middle. There is no change in the near the wall, but it flattens in the middle. That has some resemblance with the classical fluid behavior. And but interestingly, there is some experimental work which has been published recently in 2015. This is the first experimental work which have measured this normal component profile using the fluorescence technique. So here what we see that when heat flux is low, then it is almost parabolic. But instead of flattening in the middle, it flattens near the wall. But we are getting the flattening in the middle. So we are getting some totally different result what is being observed in the experiment. So when question arises that where we have gone wrong, so there are many limitations again in our model that we have not considered this nonlinear term. So we'll have to implement this term in our model, and then we have to see that whether we get this behavior of the normal component or not. That will be one task. So many tasks have been left unanswered, but we have answered some part of it. we are able to propose this dynamical equation for vortex and density in case of inhomogeneous flow, and that is of first of its kind. And next thing what we did that we considered the back reaction of superfluid component or normal component. And first time we were able to show also that it flattens in the middle, because this is first simulation in that case. But it is not consistent with the experimental observations, so we'll have to again take into account of nonlinear term and see that how it affects the system dynamics. Once we do that, then we can also understand a little bit at what can be the control parameter, because it seems that there are many control parameters here. One is the mutual friction, relative velocity, vortex line density. So which control parameter we should tune in order to get the transition what they observe in the experiment. So with that, I would like to thank you for the time.
In your movie, did you show velocity field or?
No, that was quantized vortices.
Okay,
so there is a velocity associated with that. Okay. So you can consider that if it is like straight vortices, okay, then velocity will be like a ring kind of a structure.
Okay.
So if it is changing its topology, then velocity also gets randomized.
Okay.
Any other questions? Your coupling of quantized state to the normal thing is through Biot-Savart law kind of a thing?
Yeah.
Huh?
Yes. So we are solving this quantized vortices dynamics using the Biot-Savart. And for normal component, we are solving Navier-Stokes equation.
No, but the coupling from the quantized to this one would be induced velocity of this vortex, the quantized vortex on